Firstly, thank you everyone for joining. Um, Today we're going to be looking at a piece of malware called Crosslock. It was first reported on by just a random threat intel analyst that I follow on Twitter. Found a hash, said it was in Golang. I'm like, wow, this is interesting. Let's go and look at it because I've never went and looked at like an actual Golang malware binary. As you'll find out by the end, I was very disappointed. You'll probably also be very disappointed. It's literally the most unspecial thing in the world. But why are we here? Because Golang's kind of dumb and stupid. And that actually helps out threat actors because the programs that we're used to using for, decompiling and analyzing binaries mess up. They don't work because, its assembly structure is incredibly atypical compared to something like a C++, which most modern decompilers are geared towards. Now, that also goes to say that there are many people and groups that have published content as scripts or plugins for both IDA and Ghidra that make reversing Golang a lot easier. In this specific binary, after a little bit of working and testing, I ended up using GoReSim, which is a tool released by Mandiant. It is available on their GitHub, and then an extension to Ghidra called the Golang Analyzer extension. And a fun, neat little thing about the Golang Analyzer extension is that it actually has decompilation capabilities, which is why you can see this code right here actually looking relatively nice. Like you have normal function calls, right, to main.onHook, main.createFile. There's still weird Golang stuff that remains and that will always remain, but you have generally a pretty decent overview of what the functions actually do rather than having Ghidra try and apply, C logic to Golang code, which, as we will kind of notice going further into the depths of what Golang does, especially at the assembly level, we'll notice that a lot of things are really, really weird and don't make sense. But to start things off, I put us into main.main because, that's kind of where most things start. So the first thing that stands out is this weird runtime, more stack, no CTX thing. You'll find this at basically every subroutine that exists within a Golang binary, and that is due to the fact that everything is stack-based, and weirdly, everything can be accessed at the same time if wanted to be, but that's why you have these kind of quote-unquote mutex locks that prevent those things from happening. But these kinds of things can be essentially fully ignored when analyzing a function. Parse args we'll go into a little bit later because this binary is actually a debug build, not like a quote-unquote production build, because they do have their debug strings still left in here, which is partially due to the fact that they use basically just an open source EDR evasion tool and slapped some basic ransomware stuff on top of it and called it a day. So let's look at main.onHook first. This is where one of the weird things of Golang assembly first pops up. So if we look at these two statements here, we get the current process ID and then we call open process. But the parameter passed to open process in the first parameter, we would usually expect that to be the handle or the process ID. But Ghidra says we're actually passing OX1F0FFF into it, which, with a little bit of experience, you can kind of tell that that is actually an access mask for open process rather than the handle. And that is because if we look at the actual raw assembly down here, the baseline assumption for any function call is that the first parameter is going to be stored in EAX, which, again, Ghidra also assumes, thus putting the access mask into the first parameter of open process. But if we look at the actual return value of get current process ID, which is the value that we're expected to pass into open process, that is going to be returned in EAX, but is moved into ECX before we call open process. So in this case, ECX is actually holding our first parameter, whereas EAX is holding the second parameter. This then therefore breaks the decompilation up here. But if we look at the raw assembly and have a general understanding of how WinAPI works, we can kind of mentally work our way around that. But continuing on the whole idea of this being a debug build, we have this lovely main.print debug, which indicates that they're debug printing. This brings in another kind of weird thing with Golang. So Golang strings are not really a string, they're rather a structure in memory. So if you think about how like IDA or Ghidra by default search for strings, they're looking for things such as null terminators, right? But Golang strings don't have null terminators. As I said, they're stored in a structure, so you have a pointer as the first item of the structure, and then you have the length of the string as the second item of the structure. So if you see calls that deal with strings in general, somewhere within the call or within the conversion call before it, you will always have a length passed to it. So initially, when I was analyzing this binary, a lot of these strings here were just named to random, global variable data names because they didn't have a null terminator. Thus, Ghidra didn't think they were an actual string type. This can still then afterwards be circumvented due to these function calls. So what you can do is you can just retype your global variable by pressing Control L. And the neat thing is that although I did it in decimal here, you can also just pass the length as a hex value. So you don't have to deal with any of the conversions of that. You could just do character 0x26, since that's the length for print debug, and it would properly type it, and you will now have a string here that's a lot easier to read. That is a process that very much can be automated, especially if you know the specific functions that are being used for those operations. One thing I cover in my article that I'm currently writing on this is the usage of runtime dot convert t string instead of convert t64 here. But that function works in the same exact way as we had in print debug, for example. So you'll have your pointer to the string as the first argument, and then the length of the string afterwards. If once we go a little bit into other functions, we will see this conv t string pop up a lot more, and it will hopefully make a bit more sense then when I cover it. But going back, this main unhook basically just make sure that there are no hooks within the event tracing applied to the binary itself. That sounds a bit weird now, but hopefully once we go deeper into the binary, that'll make more sense. Next thing that I want to tackle is main.magic, since this is a function that probably isn't too well known, at least that I know of as being like a standard function call. But this Golang binary was also the first time that I saw it myself, so I'm just going to try and go through it the best that I can. So one of the big quote-unquote evasion tactics that Crosslock uses is that they will spawn a different process. Well, okay, not Crosslock specifically, the open source evasion library that they're implementing. They essentially create a process that loads ntdll.dll, finds the base address of it, and then the offset to the .text section. Then from finding the .text section, they will actually take that memory section and write it into their own process so that they can call the functions internally without making a direct Win API call to that, which could potentially be caught by EDRs. So a lot of the code that has a common tag of evade.go is really just an implementation of that open source library. I didn't know that until a decent bit into my analysis, so I spent quite a long time analyzing this. But to save you all time, these debug statements, these debug print statements, are basically what are the dead giveaway of this being just the open source library, since these exact strings do show up in there. But that is main.magic's kind of purpose. As you see here, we have the call to write process memory. We're talking about the hooks being flushed out, lovely. And yeah, there's not really that much more to that one. Main.init is a bit more interesting in that regard. So as I was talking about earlier, there is this lovely call. Where is it? Is it in here? Oh no, that's this way. Okay. So main.init uses stack strings for God knows what reason, to quote unquote try and obfuscate the strings that they use. Initially, the first couple calls deal specifically with setting up the README after decryption, which stores the README text, as well as their tox ID. But after that, what they essentially do is they load NTDLL. They load in the pointers for NTRVM. If you don't know what that is, NT-read virtual memory. If you look at the assembly structure for it, once again, things are going to be loaded into RCX, which is just the 64-bit version of ECX. So once again, we have that weird kind of structuring where our parameter is actually going to be in the CX register rather than the AX like it would usually be. But again, once you know that, you can apply that and you can go through to essentially find all of the actual strings that are being used. And then eventually some of them are set to global pointer variables, some of them are only set to local pointer variables. But again, their quote unquote obfuscation for this is using just stack strings, which can also be automated away, but you can just hover over it in Ghidra and it'll tell you the conversion at the bottom. Yeah, that's really all I did for this one. And there are obviously, IOCs and rules that you can write for this specific function, but in the end, they would just mirror exactly what you would write for detection rules if you were to write detection rules for the entire library that they implemented. So we go back to main.main, because obviously this is where the important stuff happens. Here is some of this runtime.convert to string stuff that I was talking about. So as you see here, we have our call, we have our pointer to the variable, and we have the actual size of the string that's going to be loaded in. So if we go here, UAC bypass was checked. If you're looking at the raw assembly here for the global variables, the ones that have like char and an actual number are ones that I manually set, or had to set while going through the binary. Ones like these, oh no, I didn't do that one manually, but other ones are automatically detected by the analyzer extension plugin. Again, it's not perfect. Golang is a weird language. You still have to do quite a lot of manual work to actually get things to a level that is fully understandable. But again, this specific call to conv string is actually a just generally really good indicator of where an actual string is going to be loaded in. And just again, to reinforce that strings are a structure, we always have the value from the address, right, loaded in because we're using LEA, and then the actual length that comes into there. But as we check out here, we're kind of just doing some baseline default checks. These global variables, if we look at here, they're written to within parse args. So essentially, they're just checking for whether certain arguments are enabled or not. It looks a bit weird in the disassembly because you're checking against, /0 like a escape character. But if you look at the xrefs, they're essentially just checking for certain values passed within the arguments. But if we look at the innermost if statement, we get a check for is admin. Again, we have our local more stack, no context, but we see this allocate and initialize SID, which has quite a lot of parameters passed to it. But realistically, we don't have to fully figure out all of the parameters for this because or at least I, from experience, know that we're just looking whether or not our SID is part of the admin member, like the token itself. If it's not, we simply return false. And from there, we have this check here for extra out AL. So again, the return value is going to be in your AX register, so EAX, RX, whatever. AL is just the lower bits of that. So if we're not an admin, we're going to try and priv escalate. Makes sense, right? Oh, look, we also have a string here, gaining admin rights. Okay, cool. So this is where we kind of get into some of the IOCs that we can look for, or for the real blue teamers, ETPs, because fucking MITRE attack framework and shit like that. I don't know. But as if it's 2016, we're still just doing stuff in the registry. So execute command is just a function that will eventually call cmd.exe with the /c parameter. I forget exactly where that is in here. But it is essentially just a function, to call cmd.run. That's all it does. So if we go back, this is going to look weird here, but this whole kind of thing is a very well researched UAC bypass by sideloading a binary into the event viewer process. Hold on, let me go to the article. It was first talked about in 2016 by a person that goes by Enigma 3, or Enigma OX3, sorry. But yeah, you basically just put a path into the registry of mmc.exe, and then anytime eventviewer.exe is run, it will actually get sideloaded and give you a UAC bypass. Then we're simply going to delete the registry key, and we now have our binary running as admin. Ta-da! Really, they're not doing anything fancy here. As I said, it's a 2016 technique. It's kind of sad, but that's a privilege escalation. Fun. We keep going down here. We have this cleaning string. Okay. Well, I wonder what they're cleaning. Okay. So they're calling to runtime new proc a bunch of times with pointers to other functions. If we look at main.rvss, once again, we are simply calling into execute command with a string. This time, we're using VSS admin to delete shadows All of these functions that we'll be looking at here for the cleaning process are also things that, as far as I know, are literally copied from WannaCry, like one for one copied. Like it, I remember reading the white paper or the original one for the WannaCry analysis, and I'm pretty sure the order even of like the WB admin deletes was the exact same as it is here. So as we can see, um, the, the TA that's behind this is quite proficient at leveraging open source information for their payloads. Quite proficient. But again, that's kind of the general overview that I got from this binary, is that there really isn't anything special about this. The only thing special is that they use Golang. Um, and again, this is just basic ransomware stuff. They stop a service, SQL Server agent service. Um, if we look to references to it, um, there's just one unconditional call to it. Like, I don't know. It is just kind of sad to see how little they do, um, because I had high hopes for this. And the one really interesting part that I want to note about this is that apparently this is supposed to be a double extortion scheme, but nowhere in the binary is there any capabilities to actually make remote callouts to a server in any form. The only thing that slightly could hint at the fact that they're still doing a double extortion scheme is the fact that they have the option to authenticate to a remote host for some sort of lateral movement. If only the world would be so great and we could actually open source our threat intelligence, I would be able to download the two other binaries and hashes that are associated with this campaign. But due to the fact that I am not working for a large threat intelligence company, I'm blocked from downloading them on VirusTotal. So all of us are kind of left in the dark about this. All we know is that these people just stole some EDR bypass code from GitHub and wrote a little bit of 2016 ransomware around it.
And
Because,
that's kind of the norm, right? Just kind of taking that
yeah,
base code and reusing it.
because unfortunately, it works. Like, the reason we know about Crosslock existing is because it worked. Like, the company that they targeted went down. They got their files encrypted, which, again, sad, very sad. Because in my mind, when I saw these strings here, like, in what world should even like Microsoft Defender not pick up on this as being like a potentially malicious command? Like, how are you able to hard code this into your binary in a non-encrypted string and just run it via a basic command line execution via the native language itself? Like, we are calling os/exec.cmd.run. Like, we are using Golang natively to call to the CMD to run, a destructive script that since 2016 has been associated with being used by ransomware. Again, not going to turn this into a whole philosophical talk about the state of modern cybersecurity, but as a reverse engineer, it is always fun to know that it might be 2023, it might be 2025, it might be 2030. You'll still probably see bypasses from 2016 being used and them working in the wild. So, in terms of actual functionality uh, within the binary, there is not really too much more that relates to the malicious actions itself. You have a few things that are related to the cryptography that they use. For example, in here, we're specifically generating ECC keys because they're using, I think, Cha-Cha 20 it was. Um, I'm pretty sure there's a reference to it in main.main at the start. Yeah, so we're calling into the cha utils. But from my perspective, this is one of the only things that's kind of unique about them, in terms of the fact that they use this algorithm for their cryptographic encryption. But yeah, you know, it's not really like that big of anything. You have some basic code that if you have worked at any form of game cheating, you'll know is just trying to find a handle to a process. So, we have create tool up there to snapshot. That's in, every single C-based example. Since Golang will just call into the Win API, you can replicate that pretty easily. There are a few other functions that kind of remain unnamed for myself because they don't really do too much. Um, so in these, for example, we see that we're calling into the cha utils for encrypting stuff. Here, this is just another subroutine for crawling the disk for files, which again is all just very much baseline standard ransomware behavior. Nothing that honestly stands out in any way. And beyond that, uh, terminate proc again doesn't really do much special. The only kind of reason why these things work is the fact that they are using a UAC bypass. If you were to simply call like terminate process and close handle from a non-elevated binary to an actual important process, you're gonna get blocked by most decent systems. But again, we prevest, we bypassed UAC. It's all good. Personally, from my own standpoint, process termination and stuff like that are areas where you can get really, really, really creative in terms of what you can do to destroy a process or to hide a process or any of those kinds of other things, which is what I was hoping to see in this binary. Again, truly, truly disappointed. But there really isn't that much else left in terms of the binary itself. The main focus that I took away from this is actually understanding how to analyze Golang in an efficient manner. Because even with the plugins, as I was saying, the decompilation looks a lot nicer, but it still doesn't make actual sense. Like, this does not in any way represent the actual Golang code that runs behind this. Because, again, the best Golang dev I know is our lovely Totally Not a Hackster, and he has not once in his life used runtime.conft string in an actual program. And if he hasn't, I don't think anyone has. So, part of what the future plans are for my own personal research are using these internal calls that I was talking about to not only aid in string analysis, but also to eventually just kind of remove them from the decompilation window and integrate the Golang internal calls for anything runtime dot, for example, into the actual proper function calls that we care about, like for example, format.fprintf. Um, the printing functions in Golang um, are also quite weird because once again, it all comes back to the fact that strings are incredibly weird. So this is not something that I'll be covering in here necessarily. It's something I'm covering more in the article. But if you have any sort of format.print calls, you are going to be focused, you're going to have a lot of kind of global data references. So if we look into the assembly here and compare it with what we have in the decompiled function call. Um, we have a ton of global pointers. This one is just going to be the format specifier because you can kind of see it's %s/n. So those kinds of things will remain as being kind of normal indicators of format strings. But something that you won't necessarily see in like a C-based fprintf is this reference to the data type writer, then eventually this random pointer here, which is also just that. Um, right here, it's undefined because it is actually something that is written to at runtime rather than at compile time. But again, these are all things where eventually you just kind of have to click through what is actually being loaded into the parameters in the assembly, because once again, the assembly of Golang is incredibly atypical, and you just won't be able to rely as a whole on the decompilation window.